Okay, good morning and good afternoon to everybody. My name is Asfandyar Kuhi. I'm Simulation Product Manager Technical working with John Belsham. And today's webinar, we're talking about the plastic injection molding using SolidWorks Simulation capabilities. All right, the first thing we have to mention is in SolidWorks Simulation, as you've been let's say participant to our previous webinars, you know we have a complete product simulation solution that is including your SolidWorks FEA analysis. We'll be talking about the structural analysis. Also, we're talking about SolidWorks flow simulation if you are doing any flow analysis or thermofluid analysis. And also, we do have SolidWorks Plastic, which is the topic for today. And if you are in the business of making any mechanism design or rigid body motion, then we have SolidWorks Motion. So looking at the range of the product, the main advantage you're getting with SolidWorks is its full integration with your 3D CAD. Well, you have your design and your simulation all in one file in a different tab. You can manage it, and whatever updates you make or design change you make to your, let's say, design and components or assemblies, it is going to update everywhere, including your simulations. So we have a fully coupled simulation add-ins to your CAD package. They are very powerful and robust. There are so many benchmarks and real-world examples for our result. Well, so many industrial partners are using those solutions. Now, as we said, specifically, we're talking about SolidWorks Plastic today and have an overview and introductory, let's say, overview to SolidWorks Plastic capabilities. Now, before we go into any details, let's highlight what we have as a licenses or different capabilities of SolidWorks Plastics. The entry package with SolidWorks Plastic is standard. Well, as you can see in this package, you can have your model and mold design and looking at filling time and short shots, air traps, sink mark, multiple gates design, and weld lines. These are the highlights. There are more when we go into the case study and we can have a look. There are so many subcategories on this one. However, if you like to extend the capabilities of SolidWorks Plastic and extend it to SolidWorks Plastic Professional, you are able to do multiple cavity, Ronald balancing, shrinkage, insert and over moldings, cooling time estimation, gas co-injection and valve gates, co-injection and fiber analysis. And for those who are into the business of warping and advanced cooling analysis, they have to upgrade their license to SolidWorks Plastic Premium. Today we are focusing on SolidWorks standard capabilities. We have an introductory, let's say, case study, and we're looking at the procedure and these result as an outcome. However, if you are interested on more information, definitely we can organize a private session. And also we have a full training available on all these modules within our premises in different status. All right, let's have a look to the filling time and short shots outcome. When you have a mold design and you would like to estimate how long does it take to fill a part, you have the opportunity to set and run the flow analysis and get the estimation of the time. So with this option, you definitely can achieve a couple of things. You see your results in a virtual environment and get insight of the manufacturability of your, let's say, product, looking at the pressure and temperature distribution at end of the field, frozen layer friction at the end of the field, velocity vectors, clamp force, shear rate, cycle time, and so many other details parameters. When we're talking about the next one, which is short shots, it will show you based on your selection, means your component design and thicknesses, let's say maintaining pressure, clamp force, and the machine you have used with the material assigned to it. If the whole mold is getting filled with the material and you are not coming with short shots, or if it's happening, where they are and what sort of percentage is getting fulfilled here, means we can look at the results and see what percentage of the pressure, injection pressure, has been used. Have we achieved the maximum? Is it sufficient for filling? You can visualize the front flow and see how far you have reached to your mold, and you definitely can adjust the thicknesses you have put on your design or the machine you have used. Rerunning is the option. Well, as we said, when you are doing any changes, then you definitely make a second run, and there is no need to do excessive work rather than click on run again while the parts are getting updated. All right, let's have a look to the second capabilities we can do. So it's about air traps. And basically, you know, in every, let's say, mold design and part injection, when the flow is coming to the corners and the ends, there is an existing air inside the mold and it needs to be vented. Now, using this capability, you will see where are the air traps. Well, basically, if it's desired, you can keep them and put your ventilation system there. Or if it is not, then again, you have the option of changing your injection points, changing the, let's say, design thicknesses and everything else. So we can definitely have a look when, let's say, the air trap is happening and if there is any venting to avoid burn marks on the surfaces. And also we can have a visualized regions where the air will be pushed and provide a corresponding ventilation. Okay. Now, the other capabilities we are talking about is about the sink marks. Well, basically, you know, when you're doing any, let's say, injection molding, due to the temperature gradient, well, it's causing about different thicknesses of the material, and possibly you have ribs or any supporting component. You might get a bit of mark down on the outer or on the cosmetic of your product, and this is something we definitely want to avoid. These are all called sink mark, and definitely SolidWorks can predict these, let's say, marks prior to your manufacturing stage. So it's a local surface depression that typically occurs in a molding with a thicker section or at the location above the ribs, bosses, and internal fillets. This is a cosmetic and it should be avoided. So we can have a prediction about their magnitude, location, and again, you have the option to change your design, change the injection points, and rerun until you get to the best result you want. Next thing we would like to have a look is about the capabilities of the multiple gates. So in so many cases, you might not have just one injection point, and in SolidWorks Simulation Standard, you are able to have multiple injection points, looking at the flow of your mold, and then looking at the end result about the fill time and everything else, and see how the fluid is getting distributed and how they actually filling the mold. In this case, you can have, let's say, a prediction on early stages of the product development, where you are flexible to change the location and amount of the gates. So it's not only the location of the gates we are controlling, it's also the percentage of the flow is coming from different gates. So you can definitely, let's say, prevent any failure on the early stage and do not go to a very late stage where the product is launched and you are just done all your toolings, mold design and everything else, and then you are facing with that one. All right, but now we're going to last but not least about weld lines. Well, you again having a design on your mold and you do the injection simulation here. There are some places that the two different flows are coming together and meeting, and that's basically they are creating a weld line, like the lines you can see on here, and that is the software prediction. These are the places Well, it's not just only a cosmetic effect is happening. This is where we have the weakest point of the product, and it is a potential to break along these weld lines as the let's say the mold flow is not getting fully mixed, and we have stress concentration here. By doing a prediction here, we are fully aware where are these weld lines are. We can avoid them or push them in let's say the places that they are not greatly on a huge forces, and definitely coming with a very reliable design set here. Okay. Now, as we said, this is all you can do in SolidWorks Simulation Standard. However, much more in detail capabilities are happening here, and which is not the focus of the webinar today. What I would like to do instead is go and have a look how the setup procedure is look like using SolidWorks Simulation, Plastic Simulation, looking at what we have highlighted in Simulation Standard. But again, if you are interested on the other capabilities, please do not hesitate to contact us. Alrighty. Let me come back, open up my SolidWorks, and this is the file. I do have it. Okay, this look like a plastic cover to any electronic device, or even we might thinking about a ringing bell, or even a very old mobile. It's a very simple part, as you can see. It's almost a uniform thickness, and we have a couple of holes and let's say curves on the let's say component. Now, look like the other simulation product, SolidWorks Plastic is also is an add-in. Means you might have any level of your CAD software, means SolidWorks CAD either standard, professional, or premium. And by purchasing the let's say plastic, you go into your add-in and make this one active, like what I do, and then you will get this let's say add-in active, and you will get a tab up here, and all your tools are listed. Also, you do have your plastic manager tab. Well, you can see this is where we're creating the project, putting our let's say inputs, and then we do run and see the result. Now, as you can see here, when it is an empty tree and there is no project defined, the first thing we have to do is to mesh your actual product. For those who have a bit of work with FEA or CFD, they are pretty familiar about the mesh. But basically, what we have, when you have a CAD geometry and you would like to do any FEA, CFD, or plastic simulation, you're basically converting that geometry to the network of triangular elements connecting together and representing your actual CAD geometry. So in any simulation, we don't have geometry anymore. There would be a process which is converting your actual geometry to a network of triangles called mesh. Those triangles are simply let's say sharing let's say points when they are attached together, and these are nodes, and these are exactly where we are doing our calculation. So we are going to explain this a bit more while we do the mesh, but just letting you know, in order to conduct any sort of simulation, you have to convert the CAD geometry to the network of elements, and all the calculations are happening within the element side. So we have two types of mesh, solid or shell. Solid elements, basically the elements which are three-dimensional, means they can go over the thickness, length and width and height and everywhere else, while the shell elements are basically 2D elements, means it's just a triangle sitting on one face and representing the face. Most of the plastic parts, we already know the thickness compared to the other direction is not that much significant. Therefore, there is a valid assumption, and there is not much of, let's say, sacrifice in your accuracy of the prediction if you're using shell elements. But in specific case, that could be different. But basically, you can understand now, using shell element means you just having one surface, therefore you have less elements. But if you're going through the thickness, that means you're using more elements. More elements, better results, and more accurate result in some cases, but definitely what is happening, it takes a lot of time. But when we're talking about shell elements, if they are valid, means we have very small thickness compared to the other dimensions, then they are super valid, they are all good to use, and you definitely have to define them and optimize the time. So it's better to have the answer within 10 minutes rather than 10 days. Okay? All right, so in order to create the mesh first, as a first step, you have to right click. You have the option to go automatic meshing or manual. Let's click on manual this time and having a look what is happening. The first thing is the software is asking where I have to mesh. There is one cavity active and you can looking at it and basically say this is where I want to mesh. Click next. Then you have to say what is my element size or the triangle size. Basically, you know that more, or let's say coarse element, bigger triangle means the prediction quicker but very coarse. Less means smaller triangles, so many of them, better representation of your CAD but taking some time. Let's look at the coarse one. So my triangle size is about 6 millimeters. Now I'm asking for the mesh. Now look what is happening. My CAD geometry is being converted to that network. So 6.2601 millimeter size triangle being spread out through my geometry, and it's representing every single corner of it. Now, one important fact, and it's a very important, let's say, note here. Guys, you can see this is a curve which is going to be represented by triangles, or let's say these lines, these straight lines are representing my top curve. Definitely, you know, if you have very long straight lines, you are predicting that curve much quicker, but very rough. But if you make it smaller, you are more close to the length of that arc or that curve, but you have to use more and more elements. The main idea is we have to select something optimized. Means it is exactly the amount required to put and predict the correct result. Not less, not more. Because first of all, if we're putting less, then simply we are not predicting the result correctly. If we're putting more, we're trying to predict something in a very long, let's say, time, and it is with a huge computational effort required. We have to avoid both situations. The very good thing is that you can examine this Puryear to accept it. Means if I go there, next stage, it is showing me a couple of, let's say, highlights, and the main idea is here. I do have bad elements, about 0.04% of these total elements. And the maximum aspect ratio, basically aspect ratio is you have 3 lengths on a triangle. The ratio between length 1 and length 2, or length 2 and length 3, is the aspect ratio. The best idea if we have a fully symmetrical triangle. L1 equals to L2 equals to L3. So that is the main thing. If you can achieve that one, your aspect ratio is exactly 1, and this is the perfect element. But if you have something around 9, means one length is 9 times, let's say, bigger than the other one. Well, obviously we can see something here. It might not be exactly 9, but you can see the skewed element. Skewed element means bad representation of your geometry and not a very good result. We have to avoid this. Therefore, always we can get back and come here and, for example, put 3 millimeter for the triangle side, mesh, and this time have a look. Now you can see your CAD geometry is getting presented much better, smoother, and you are predicting all the curves, all the corners there. Your result would be more valid. In this stage, you have the option to change the overall, let's say, setting or triangle size on the whole component, or if you like, you can make a very coarse one and then locally refine anything. So this is not the highlight or a topic for today, but I'm just letting you know your refinement could be just on the curves or the corners you want as local refinement option. Set or auto, you're letting the software to go and have a check to your geometry. If somewhere requires finer mesh, it will do. Otherwise, it's sticking with your coarse element size here. All right, and also you can have a control over its graduation, means how fast from the fine to the coarse element we can move. All right, now let's have a look to the report here and see what we have. Now we're reaching to 0% bad element or 0% very bad element. Maximum aspect ratio is 3, which is really acceptable, and it looks that our mesh is working perfect. Alrighty, so I'm clicking OK. Well, you can see you have advanced tool later on to analyze your mesh, edit your triangles and single elements or even their nodes to merge them, insert more, let's say replacing and everything, which is a very powerful option you got if you have any, let's say CMM data or STL file with lots of error on it and let's say faulty corners. So definitely you can go and let's say merge the node, delete the bad elements, recreate them, and this is a very, very powerful tool, and it's very advanced topic here. It might require a bit of time, but end result might be really fantastic. All right, now by clicking OK here, what would be happen? My project is created. And you can see there is a green tick on the shell, means my CAD geometry is now being converted. I do have my shell element with the settings output. Now looking at what happened to the tree, we have input section. There is an advisor section, which always can assist you, run and results. So these are the main things. So we have to say, what are my input or what are my boundary conditions look like? We can always get an assist from the software. We're running the project and we're looking at the result. Let's expand the input section. In your input section, what you can see is the material definition. So right click and you have to say what sort of material I have used. There are some which is my favorites, but I can go open database, and this is a real asset of SolidWorks Simulation Plastic, and it is let's say available from the first level to the end. Well, you can see all the families of the plastic, about 115 different plastic type are all been listed, and under each category we have the material listed. You can see, for example, in ABS family we're talking about exactly 529 different from different manufacturers, different grades and everything else. I can't imagine something which is not existing here. That is a very fresh database and always getting updated. You can sort by family, or even you can sort by a company, means different company who are developing. And if you are just getting your, let's say, materials from there, you can go and find their family products and definitely pick up any of them as you might like it. Alrighty. Now, looking at any materials, what sort of information is listed in material property? The first and very important one is the viscosity related to shear rate. You are getting the PVT, which is 1 over the density regarding to temperature, specific heat values, thermal conductivity, elastic modulus, Poisson ratio, and also the polymer material parameters. And you can see the list of all of things you can see curling module, which is not here, shear relaxation module, and also thermal expansion coefficient, which is fully tested and fully valid properties. This is a very good news for those who are really looking on doing an FEA study or a structural test after they've done the SolidWorks Plastic Simulation completed. Means yes, I know it is manufacturable and it is coming now. Now I would like to let's say have a structural test afterward. Well, all the information you need, such as elastic modulus, Poisson ratio, and thermal conductivity, specific heat, and etc., is all here. And there is no need to go and find the material properties and put it in your FEA studies. That is again a really valuable asset here in SolidWorks Simulation Plastics and can be beneficial directly to itself or any other cooperative studies here. All right, but just in case you can have your user database and add anything to your favorite, let's say material, or even add a product yourself, add a material yourself, delete them, edit them, and everything else. So you have the option to do this. Alrighty. Now, from this point, what we have to do is basically, from anything we would like to choose, we basically go and assign it. When you do that, there is again a green tick mark where you can see my material has been assigned here. Okay, now we are into the second section, process parameter, and you have fill setting and you have a pack setting. So as you know, in any molding process or injection, you have the fill, you have the packing, and then it is on clamping. About the fill setting, right click and open setting, you can set so many, let's say, important parameters about the filling time, what you're estimating, or if you like, you can basically leave it alone and say auto, let the software to run and find it for you. Melt temperature, mold temperature, and injection pressure limit means what sort of pressure you are maintaining in your mold based on what you know about your machines. If you like, then you can go to advanced, and the first thing I would like to mention is the machine database here. And again, you can access a huge database of existing machines with their, let's say, description, injection unit description, clamping unit description, hydraulic units, and general. Again, this is a second asset, means you don't really have to worry about what are my specification of machine. If it is being manufactured, is listed here, you definitely can do. You have the find option, put in the wording, and see if it is listed here. Also, you can have your own profile set for the feeling stage, means what is happening on 0.4 second of the injection and what sort of percentage of the flow rate is coming, what is happening at 0.8, 1.2, 1.6, and 2 seconds of what software is picking up is the total of 2 seconds for filling. It's going to test that one, and it's look like the same flow rate is coming there. But you definitely can adjust it. Say, for this proportion of time, I would like to have 20%, and for the next one is 40% is coming. I have variable injection flow rates coming to my mold, and this is what I want. What else we can do is, be setting all of this in our field setting, and basically that would be the same on your packing setting. Well, you can say pressure holding time. Again, you make it as an auto one, pure cooling time, or in your packing, if you like to make a, let's say, curve or any, let's say, function built it, that is how does it look like. And you can see this time it's not a flat line, it is look like this. Now that is means I need to have the SolidWorks Professional Simulation Plastic Professional to go over the packing as well. But this is again, it's not our focus, but definitely you can make the setting finalize here. All right, so these are the, let's say, process parameters, and we are now talking about the boundary conditions. Well, we're specifying flow injection factor, modify local thickness if you want, and most importantly is the injection location. So right click and open setting, you are going to decide where my mold is coming here. You definitely can go and pick up a line or a surface or anywhere else to add your injection point. If you don't like it, you go and select the other place and say this is where I would like to put my stuff there. You have a control about the pointer diameter. For example, 5 millimeter, you can see obviously it's bigger. And you can tell the software what percentage or what sort of ratio of the injection is coming from this location. Start 0 and 100%. I can change it to anything. I might have different injection points and assign any percentage to any of them. If you like to add this one, then add injection location. Otherwise, you can go and delete or delete multiple. And the very good thing here is you can have a prediction of the flow pattern before even you go to run and spend some considerable time here. By clicking that one, it is showing you which areas are getting filled first, basically build, and which areas are going to filled at the end. It looks very obvious in this case, which is a very simple part and one let's say injection point. But you can imagine if you have multiple injection points and more complex shape, and you would like to know how your let's say flow is going to distribute it, and what sort of filling let's say distribution you will get before you go and for a couple of minutes or a couple of hours even run the project, you have a bit of prediction here. That is a very good insight, and in earlier stage of even simulation we can go and correct ourselves if it's required to change the thickness, location of your let's say injection, adding more or less. This is exactly what we can do. But if you're happy with the setting, yeah, then click OK and we're done. So we're almost done and we set up everything here. Our material, field setting, if we are doing packing setting, and our injection location. Now it's the time to run the project. Well, if you have a look right now, because my let's say license is not let's say premium license, I can see the flow, and there is a flow and pack, which is the professional license. Right click on that one, run. What is happening? The model is getting prepared, and it's basically looking at the progress, and simply when it's starting, it is showing you an interactive section, let's say scenario and figure where you can see how your mold flow is moving and basically how it's merging, and you might predict something from the beginning here. What is happening, how the mold flow is let's say moving. The other information, you can see the cells fill 30%, the process at the time is 0.67 seconds, and the maximum injection pressure we have reached up to this point is 4.28 right now megapascal. That is what we have used. Okay, now we have to wait that this is all finished, and basically you can see the pressure is increasing, and it's make a lot of sense. You need more pressure to push the flow until it's reached to the end. Well, up to this point, 70%, and it looks that we are just fill everything here. All right, so it's let's say last couple of iteration required, and let's see what is the final result look like. Okay, all done, perfect. The first thing you can see is there is a result advisor section coming to you and giving you a very good and basic information. This part can be successfully filled with an injection pressure of 8.8 megapascal. The injection pressure required to fill this is less than 66% of the maximum injection pressure limit specified for this analysis, which means that you are well under your specified limits. Means I'm more than okay here. So either I'm deciding of multiple cavities, either I'm deciding to just move it to the let's say smaller machines, less expensive to run, and etc. Well, basically, as you can see, the first thing we are looking at here is fill time. It is showing us is 1.7071 seconds required to this one injection here. You can do the animation if you like, and looking at this while it is as a mold, or if you like to see the ISO line feeling, that's up to you. So it's showing the regions of the fluid as the ISO line with a different pressure and temperature. You can adjust the speed of your animation, stop it. And the other good things you can see here is very, let's say, good information, such as velocity vector at the end of the field. Well, you can see all your mold flow is shown by velocity vectors, their direction, their flow, and their magnitude. So we're talking about maximum of 2.4698 centimeter per second happening at the entry, and average here about 0.4940 on the rest of the other model. The other thing we can have a look, as we said, and it's very important at this stage, is about the weld lines. Well, we definitely saw it in the filling time, and we saw these are the weld line. Two different mold flow are just merging here, and they create a weld line, one here, the other one is here. Now it is our decision to accept as it is, looking at their, let's say, magnitudes in degrees, say yes, or no, I have to go back, change my injection location, change my thicknesses, and redesign everything from the beginning. Well, if it's a significant thing or not, that is absolutely your decision. Okay? And the last thing I would like to show here in the fill time is about air traps. Well, now we obviously can see, well, when let's say the flow is merging and we get an air trap here. Well, you can see I can pause it again at that point, hopefully. Not a bit before. If I can go, let me see. No, unfortunately. You can see these two flow are merging and then pushing. That's where exactly you get the weld line, and this is your air trap. So this is more than important to understand. Again, it's your decision as a let's say, designer. This is the place I can put my ventilation system or not. So there are two facts here. I do have weld lines. I do have air trap. Should I reconsider or not? That is a different issue. Okay. Now we're talking about the fill time, and we have explored about the velocity vectors, weld lines, air trap, and see the filling time and its information. There are lots more things you can see here. For example, pressure at the end of the fill, and you can see most pressure is happening here as it is your injection location, less pressure at the end. The temperature at the end of the fill, also the average temperature or the bulk temperature at the end of the fill. There are so many other things like as cooling time, that is how much time it's required, and giving you some estimation without really going to the packing stage of what sort of time frame we are looking. 5.0092 to 5.9349 seconds. This is the cooling time and variation. We talked about sink marks. Well, definitely we can see there are some here at these locations, and it is talking about 0.0452. Is something acceptable or not? Again, it's back to the designer to accept it. If not, definitely would be a thickness analysis, reshuffle or redesign everything, and coming back to your let's say running the project. Same on any of these. If you like to look at the weld lines or the air trap, it is also again possible. Well, you can have a judge. There are so many other, let's say, parameters we can review together, such as ease of fill or gate filling contribution or frozen layer at the fraction of the end fill. So how might be the possibility of freezing of your flow, and you can see here from 0 to almost 0.25. Well, that is a very acceptable range, and it doesn't really showing us any bad sort of results. Alrighty guys, so this is what we have, and this is an introduction to what we're trying to do and what we can achieve in SolidWorks Plastic, let's say, studies. Well, the capabilities of the software is way beyond what we said, and there are so many real-world, let's say, examples, but I would like to bring it to the screen, and you can see these are the projects done by using SolidWorks Simulation tool. And you can see the short shots, what has been predicted using SolidWorks Simulation Plastic, and this is exactly what is been happening. It's a very, very good overlap between the result and predicted result. So real world result you can see here, and these are the predictions. And interactively, the next slide is also showing us fairly the same manufactured from it's not fully filled to it's completely and perfectly being manufactured. And it is all showing us the, let's say, a good example of how we can really, let's say, omit our costs before we are even going to the tooling stage, and in the design stage, we're predicting everything fantastic. Alrighty guys, I would like to thank everybody for attendance and listening. Please email us, John Belsham or me, if you have any commercial discussion. Definitely go to John Belsham. If you need more technical information, either going to him or me, we are more than happy to take your, let's say, question, organize any session to see more in this product. And also, if you like to attend our training or looking at our training topics, we are more than happy to explain it. Thanks everybody, and hopefully we're starting a new set of webinars for next year, and hopefully we see everybody there. Thank you so much and have a great day.